Welcome to another class. So today we're going to be looking at past questions in line with motion. Okay, so in the description below you're going to get a link to the PDF file for the questions. Try to solve on your own first. Okay, task yourself with trying to get answers for these questions before you attempt coming along with us. Okay, it's going to help you build up the ability to tackle these questions on your own. When you make mistakes and you get corrections, then you get to know what to do next time in the occurrence of similar circumstance. So the first problem we have here is the slope of a linear distance time graph represents A, acceleration, B, displacement, C, speed, D, velocity. Okay, so which is the answer? We know we have a distance time graph. The slope of a distance time graph will always be C, speed. Okay, so we have the answer here to be speed. Alright, so number 2, we have the term rectilinear acceleration means the rate of increase of A, velocity along a circular path in the unit time. B, distance along a rectangular path in a unit time. C, displacement along a straight line path in a unit time. And D, velocity along a straight line path in a unit time. Of course, we know rectilinear motion is a one-dimensional motion in a straight line. Okay, so and then we know that acceleration is change in velocity with respect to time. So we have the rate of increase of, okay, the rates has to do with time. So the rate of increase of velocity along a straight line path in a unit time. First of all, when we see acceleration being defined as the rate of increase of course, we know it can't be distance, it can't be displacement. It has to be velocity. So we have only A and D having velocity. So this is A is velocity along a circular path in a unit time. Rectilinear is not circular, it is straight line. So D has to be the answer. So the answer is D. Okay, velocity along a straight line path in a unit time. Alright, so 3, state 2 deductions that can be made from a displacement time graph. Okay, if we have a displacement time graph, we have something like this, where this will represent distance or displacement and this will represent time. Okay, so if we have this as the graph, so we can see that one of the things we can deduce from this graph is the velocity. Okay, so if we find the slope of it, of course we're going to get the velocity. Okay, remember in number 1 here, the slope of a linear distance time graph give us speed. So for displacement time graph, we'll get velocity. So one of the things we can deduce from a displacement time graph is velocity. Okay, another thing we can deduce from it is the distance traveled. Those are 2 things that at least should come to mind. Okay, once you hear the displacement time graph. Let's move on to number 4. The time rate of increase in velocity is called, of course, it is acceleration. Okay, alright, so let's move on to the next question. We have number 5. The diagram above shows the velocity time graph. The statement that is true about this motion is that the car A decelerates between points F and H, accelerates between points F and G, has a constant speed between points E and F, has no acceleration between points F and G. So let's look at this. Decelerates between points F and H. This is point F, this is point H. This is wrong because between F and G we have constant velocity, and G and H is where we have retardation. So if there is any deceleration, it has to be between G and H, but we have F and H here, so A is wrong. Accelerates between points F and G. There's no acceleration here. This is constant velocity. Okay, the velocity is not changing. It's not changing with respect to time. It's constant. So that's B is wrong. C has a constant speed between E and F. this is E and F. Speed can't be constant here because, of course, velocity is changing with respect to time. You can see between E and F there's change in velocity, so you can't have constant of speed there. So between, okay, D is now has no acceleration between points F and G. You can see that points F and G is constant velocity, so there's no acceleration because acceleration is change in velocity, but here it's constant. So our answer is D. Okay, so move on to number 6, and there we have, from the velocity time graph shown above, which of the following quantities cannot be determined? A. Deceleration. B. Initial velocity. C. Total distance traveled. D. Initial acceleration. Okay, so if you look at this graph, we can see that we can determine deceleration here because this line here is the line that represents deceleration. Initial velocity, of course, this is the initial velocity. It's at the point 60, so where it starts from, the velocity at the point it starts, that's the initial velocity. We can deduce it from the graph. So total distance traveled, we can deduce it from the graph by finding the area under the curve. Okay, we're going to get the total distance traveled. The only thing we can get is initial acceleration. Okay, because here there's no even acceleration at the initial point. It's just velocity, constant velocity over a period of time. So initial acceleration is what we cannot deduce from the graph. So that is our answer. Number 7. Calculate the total distance covered by a train before coming to rest if its initial speed is 30 meters per second with constant retardation of 0.1 meters per second squared. Let's get to know the variables we are given here. Okay, so first of all, from this, we are given the initial speed of the train to be 30 meters per second. All right, we are also given the retardation or the acceleration to be minus 0.1 meters per second, or the retardation to be 0.1 meters per second. So acceleration is negative when it's retardation. So whenever you have retardation, acceleration is negative of that value. So we have a retardation at 0.1 meters per second squared. Acceleration automatically becomes minus 0.1 meters per second squared. Okay, so we have our final velocity to be 0, and then we have to find the distance covered. All right, our final velocity is 0 because it's retardation and the train comes to rest. If it didn't come to rest, then we can't assume 0 for final velocity, but it came to rest. All right, so we're asked to find the total distance, okay, of this train given these variables. All right, so as usual, the formulas for motion should flash before your eyes, and you need to pick one that can easily solve this problem using these variables. So we'll go for v squared equal to u squared plus 2as. All right, so if we put in the appropriate numbers in their place, we're going to have, of course, final velocity is 0 meters per second squared. We have u, initial velocity or initial speed, to be 30 meters per second, then the square of that, of course. Then we have 2as. Now, because of the negative acceleration, this positive becomes negative. So we have 2 times 0.1 meters per second squared, all right, times seconds. Okay, so if we simplify further, we have, of course, all these, which is 0.2 meters per second squared, s would move, we could move it over to this side, it becomes positive, and then we have only 30 meters per second on this other side. Now, if we simplify further, we have 30 meters per second will give us 900 meters squared per second squared. Of course, remember, okay, I made it very clear here how we work with units to get the final unit for our answer. Okay, just in case, all right, you're not conversant with that. Okay, so this is how we work units to get the unit of the final answer. So going a little bit backwards, here we have meters per second, all right, for the final speed. Okay, it is squared. Okay, but finally we have 0 here. So 0, anything multiplied by 0 is always 0. So this place is 0. We have 30 meters per second and it's squared. Okay, here we have 2 times 0.1 meters per second squared times s. So that gives us 0.2 meters per second squared. All right. Okay, but here, this squared affects both the units. Okay, don't forget, it always affects the units. All right, so we have 900 for 30 squared, but then we also have meters squared and per second squared. Okay, so moving on. This becomes, making s a subject of the formula, it becomes 900 meters squared per second squared divided by 0.2 meters per second squared. Okay, now if we simplify this, the units, we'll see that these meters here would take out, of course, 1 meter above there, so it becomes meters and not squared. This s raised to the power minus 2 will take out this one here, so you'll see that what we have left is meters. All right, then we now go on to divide 900 by 0.2 and we'll get 4,500 meters. Okay, 4,500 meters as our answer. Okay, so you see the option is B. The answer is B. Okay, so number 8, define uniform acceleration. All right, this is from, of course, WAEC exam paper 2. Okay, so the first definition I would give is, it is the equal increase in velocity at an equal interval of time. Okay, it has to be equal increase in velocity, equal interval of time, because it's uniform. Okay, this is very key, very key. Okay, equal increase in velocity, equal interval of time. That's what makes it uniform. All right. Okay, so the next one I would also give is increase in velocity by equal amounts in equal interval of time. So you can still see that this equal has to be for both quantities. All right, it has to be an equal change for both quantities for it to be uniform. Okay, so let's move on. Number 9. The diagram above illustrates the velocity time graph of a body. Calculate the distance covered by the body during the motion. Okay, so of course we have a body that moves from this point to this point, and then from this point to this point. We're asked to calculate the distance covered, and this is the velocity time graph. So in the previous question, we were asked about the deductions we can make from a velocity time graph, and I remember saying that we can get the distance covered in that velocity time graph by finding the area under the curve. All right, so we're going to do that here now to get the distance covered by the body. So the area under the curve here is going to be the area of this square. All right, we can draw a line here, a straight line here. Okay, if we do that, you see that what we have becomes 1 square here. We have this place as a square, we have here as a rectangle, and we have here as a triangle. Okay, there are 2 ways we can solve this. We can split this into 3 shapes. Okay, solve for the area here, the area here, and the area here. Or we can solve for the area here and take this full trapezium and solve for the area there. You might know how difficult it is for some people to remember the area of the trapezium. Okay, yeah, but then to make it very easy, we can split this into 3 shapes. So we have a square, a rectangle, and a triangle. Okay, so we're going to do this one to show you how it can be done. Okay, so that's the one we're doing. Area of a square plus area of rectangle plus area of triangle will give us area under the curve. Okay, so we move on. So we can see the 3 shapes we're trying to find areas for. So we have the first square, which is one side is 4 minus 0, of course, and by 4 minus 0. The other one is the rectangle is 12 minus 4 by 4 minus 0. That's 12 minus 4 and then 4 minus 0. And then for the triangle we have 10 minus 4, okay, and then 12 minus 4. Alright, so we know area of parallelogram is length times breadth. So for the square we're going to be having 4 by 4. 4 times 4 to give us 16 meters squared. Of course, remember meter multiplies meter to give us meter squared for area. Then we get the area of the rectangle, same approach, length times breadth. So we have 12 minus 4 by 4 minus 0, which is 8 times 4, which gives us 32. Okay, so meters multiplies meters gives us meter squared. Then we find the area of the triangle, which is half base times height. So we get, of course, base times height divided by 2, alright, which is 12 minus 4, which is the base, times the height, which is 10 minus 4 divided by 2. So if we do that, we're going to be having 24 meters squared, alright. Of course, this is 6, 10 minus 4 is 6, 12 minus 4 is 8, so we have 8 times 6 divided by 2. That gives us 24 meters squared. Okay, so move on to summing the area of all the shapes. So we have 16 meters squared plus 32 meters squared plus 24 meters squared. This gives us 72 meters squared. This 72 meters squared now is the total area of the shape, but then it is also the distance covered. So the distance covered here now becomes 72 meters. Okay, so that's the right option, C, 72 meters. Number 10, a body accelerates uniformly from rest at 2 meters per second squared. Calculate its velocity when it has traveled a distance of 9 meters. Okay, so of course we look out again to see which of the formulas we can use, which of the formulas for motion would help us here. So if we look at our variables very well, we have acceleration to be 2 meters per second squared, and then we have distance to be 9 meters. So those are the two things we have, and we're asked to find its velocity, okay, its final velocity after 9 minutes. So we use v squared equal to u squared plus 2as to help us here, because of course we have the distance, which is 9 minutes. We're asked to find the final velocity at that point, which is v, and then we have the acceleration to be 2 meters per second squared. Okay, the initial velocity obviously will be 0, okay, because it's definitely moves from rest. You can see that here. Putting all this into the equation, we have initial velocity 0, acceleration 2 meters squared, distance 9 meters. So we have 2 times 2 meters per second squared times 9 meters. Okay, that would give us 36 meters squared per second squared on this side. Okay, so if you look at it critically, what we did here was multiply meters by meters. Okay, so that makes this meter squared. Okay, so plus 0 squared, which is this one, that gives us v squared. But then find the square root of both sides, so we can have v, and that will give us 6 meters. Okay, because of course this is like finding the square root of 36 meters squared per second squared. So this will give us 6 meters per second. All right, because the square root of 36 is 6, square root of meter squared is meters, square root of per second squared is per second. Okay, so number 11, the 2 points of a body undergoing a uniform acceleration are 10 seconds at 10 meters per second and 30 seconds at 50 meters per second. On the velocity time graph of the body, calculate the magnitude of the acceleration of the body. Okay, so what they're trying to say is that we have something like a velocity time graph, okay, where this side represents velocity, okay, this side represents time, and they're saying there is a uniform acceleration. All right, so uniform acceleration for 10 seconds. So let's say this here is 10 seconds. All right, and then 10 here to 10 meters per second. So it comes up to 50 meters per second at 30 seconds. So this place would be, okay, let's try to get 30 seconds here. Okay, so this is time t. While here, okay, we take here to be 50. All right, this is v. Okay, so they're basically saying that on a velocity time graph, we have 2 points of a body that undergoes uniform acceleration to be this. So this is point 1, this is point 2. Point 1 is 10 meters per second at 10 seconds. Point 2 is 50 meters per second at 30 seconds. They're asking us to find the acceleration of the body. We know that acceleration is change in velocity over time. So if we want to find acceleration, it's simply 50 meters per second minus 10 meters per second divided by 30 seconds minus 10 seconds. Okay, so this would give us, of course, 40 meters per second divided by 20 seconds, which would then give us 2 meters per second. So our answer is actually B, 2 meters per second. Alright, so let's move on to number 12. A body of mass 20 grams projected vertically upwards in vacuum returns to the point of projection after 1.2 seconds. Calculate the speed of the projection. Okay, we're given gravity as 10 meters per second squared. Alright, so of course, let's try to bring out our variables. It's usually better you write down your variables first. The problem becomes clearer to you that way. So we have mass to be 20 grams. We have time to be 1.2 seconds. And we are asked to find speed. Okay, we know that this is an equation that has to do with gravity. Okay, so our acceleration here is given as 10 meters per second squared. Okay, it's projected vertically upwards. Makes us know this is an equation that has to deal with gravity. Automatically, we know that mass isn't really needed because gravity, the pull of gravity doesn't depend on mass. We know we might not need this to solve this problem. So we just focus on time, the acceleration. How do we use time and acceleration to get speed? What formula can we use? Okay, so the one that comes to mind is V equal to U plus or minus GT. Okay, so remember that, of course, this object was projected vertically upwards, okay, and it returned back to the point of projection after 1.2 seconds. So the consideration of this time consideration covers both the time with which it traveled upwards, stopped, and then fell back to its point of projection. So we're going to consider just the time it traveled from the point of rest to the point of its maximum height before falling back down. Okay, so if that is the case, that will mean our final velocity will be 0, because from the point of projection, once it is projected, it moves with an initial speed, and that speed is depleted as it goes higher because of the pull of gravity until it gets to a point where it will stop for a moment. It will come to rest for some time and then fall back down. So our final velocity is 0. Our initial velocity is what we're looking for. Our acceleration due to gravity is given, and our time is going to be 1.2 divided by 2 because we're dealing with half of the full time duration. So we have that written out here. So if we get to simplify this, of course, we're going to have 6 meters per second. Of course, this second here is going to cancel 1 second from this side. This is 1.2 divided by 2, which should give us 0.6. 0.6 by 10 should give us 6. Okay, and then we know we're left with meters per second. Alright, so that's how we have this answer. Okay, so moving on to number 13. Okay, a car starts from rest and covers a distance of 40 meters in 10 seconds. Calculate the magnitude of its acceleration. Okay, so we have variables to be initial velocity 0 because of course, the car starts from rest. So our initial velocity is 0. Our distance is 40 meters and time 10 seconds. Okay, and we're asked to find acceleration. So the formula that will come to mind given those variables will be s equal to ut plus half at squared. If we bring in our variables into the formula, we have s to be 40 meters, okay, which is our distance. Our initial velocity is 0, okay, so we have 0 there. Then half times our acceleration, all right, which we're looking for, and then time, which is 10 seconds. We square that. So if we simplify that, we have, of course, this place becomes 0. So we have 40 meters equal to half a 10 seconds squared. So of course the 2 beneath can multiply 40. It's more like saying multiply both sides by 2. So you have 40 meters times 2. All right, and then we have times 2 on this side. So we'll find out that that 2 on this side will cancel out this 2. So giving us 40 meters times 2 on this side and leaving us with 10 seconds squared a on this side. So by making a the subject of formula, this is what we're going to get. 40 meters times 2. Then that 10 squared divides this left hand side. Okay, so that's 40 meters times 2 divided by 100 seconds squared, which is equal to a. So we go further, we have this to be 80 meters divided by 100 seconds squared. Okay, so of course we're going to have this to be 0.8 meters per second squared. All right, and you can see that the answer is B. All right, so let's move on to number 14. Two cars moving in the same direction have speeds of 100 km per hour and 130 km per hour. What is the velocity of the faster car as measured by an observer in the slower car? Okay, so we can see this is a case of relative motion. So basically it's just going to be 130 km per hour minus 100 km per hour, which will be 30 km per hour. Okay, because the faster car is moving at 130 km per hour, but the observer is already moving at 100 km per hour. So if this is his frame of reference, of course he's not going to be seeing this moving at 130. Okay, he's going to be seeing this moving at 30 km per hour because he is already 100 km per hour fast. Okay, so number 15. A car moves at an initial velocity of 25 meters per second and reaches a velocity of 45 meters per second in 10 seconds. What is the acceleration of the car? Okay, so this is simple. We have initial velocity and we have final velocity, and we're given time to be 10 seconds. So it's simple. Acceleration is change in velocity over time. So we have this to be 45 meters per second minus 25 meters per second. That's v2 minus v1. Okay, final velocity minus initial velocity divided by time, 10 seconds, and we get answer to be 2 meters per second. Okay, which is D. Move on to number 16. You can see these questions are not really that difficult. They are mostly very straightforward. Okay, once you know the formulas and you can interpret the word problems, then you're good. Okay, so if it takes an object 3 seconds to fall freely to the ground from a certain height, what is the distance covered by the object? So we see this is another question that has to do with gravity. Okay, so let's consider our variables. We have time to be 3 seconds. Okay, and we are asked to find height, but we're also given gravity. So what formula can we use to solve this? Okay, so we can use h equal to ut plus or minus half gt squared. All right, where our initial velocity is obviously 0 because it's an object that fell freely to the ground. Okay, so the initial velocity must have been 0, and we have g to be the gravity, which is 10 meters per second squared, and t to be time, which is 3 seconds. So bringing those into the equation, we have 0 times t plus half times 10 meters per second squared times 3 seconds squared. Okay, so this positive is because the object is falling in the direction of the pull of gravity, so it's positive. If it's going against the pull of gravity, then it will be negative. So simplifying that, we have of course, this to be 5 meters per second squared, okay, times 9 seconds squared, because of course 2 divides 10 to give us 5, and then 3 squared is 9. So going further, we can see that we have this second squared cancel this second squared, leaving us with 5 times 9, which is 45 meters. Alright, so number 17. A car starts from rest and moves with a uniform acceleration of 30 meters per second squared for 20 seconds. Calculate the distance covered at the end of the motion. Okay, so we're given our acceleration as 30 meters per second squared. We're given time as 20 seconds, and we're asked to find distance covered. What formula comes to mind? We use s equal to ut plus half at squared, because we have acceleration, we have time, we are looking for distance. Of course, we know our initial velocity because it starts from rest. So bringing variables into this, initial velocity 0 times t plus half acceleration 30 meters per second squared times time, which is 20 seconds. We square that. So we have 20 squared to be 400, and we have 400 times 30 to be 12,000. Okay, so we're dividing 12,000 by 2 here, so that would give us 6,000 meters. Okay, so you can see that the answer here for us is the 6 kilometers. All right, so let's move on to number 18. It says a train with an initial velocity of 20 meters per second is subjected to a uniform deceleration of 2 meters per second. The time required to bring the train to a complete halt is, so we see we're given initial velocity to be 20 meters per second. All right, okay, that's here. We're given acceleration to be minus 2 meters per second. Remember, retardation is negative acceleration. All right, so we're asked to find time. What formula do we use here? All right, it's simply v equal to u plus at to solve this problem. So we bring in our variables. We have final velocity to be 0, and our final velocity is 0 in this case because it is retardation. Okay, it's deceleration, so it means it comes to a stop finally. It starts at the velocity, comes to a stop eventually. So initial velocity 20 meters per second, final velocity 0. Okay, now we have our acceleration to be minus 2 meters per second squared times time. So if we simplify this, we're going to be having 20 meters per second divided by 2 meters per second, of course, because this 2 meters per second squared t will move to this other side to become positive. Then if we now make t the subject of formula, we'll have 20 meters per second divided by 2 meters per second squared. Alright, so these meters here will cancel these meters, and so we also see that this second will divide one of these. Okay, so this will be leaving us with, of course, this is per second, so it will come up and become 20 divided by 2 seconds. That's 10 seconds. So that's the answer for that. We'll move on to number 19. Calculate the time taken for a mango fruit that falls from the tree 20 meters to the ground. Alright, so okay, we have our h to be 20 meters, we have gravity to be 10 meters per second, and we're asked to find time. Okay, so we use the formula h equal to ut plus or minus half gt squared. Bring in the variables, so we're having 20 meters equal to 0 times t. Of course, initial velocity is 0 because it fell from the tree and falls down. Okay, so at the tree it's at rest, so we have gravity to be 10 meters per second, we have time, okay, to find. So simplifying this, we would have 5 meters per second squared t squared. Okay, then if we make t squared the subject of the formula, we'll have 20 meters divided by 5 meters per second squared. Alright, and then when we divide this, we would have 4 seconds squared. Okay, so just in case we're having a little confusion about how the simplification of units was done, considering the same thing was done in number 18, I would try to bring clarity to that. Okay, so let's say we have meters. Alright, divided by meters per second squared. Okay, I'm sure you know this is the same thing as meters second squared over meters. So this meter will cancel this meter to give us second squared. Okay, so we see that we have 4s squared here. Okay, so we find the square root of both of them, of both sides. So we're going to have root t equal to root 4s squared, which will give us 2s, because square root of 4 is 2, square root of s squared is s. So we have our answer as 2s. Okay, so that's about it for this video. I hope you were able to get all the questions when you tried solving on your own. Okay, if you didn't, it's okay. Just continue trying to solve more questions on this motion topic. Alright, and I will see you in the next video. Motion continues in the next video because we're not done with it. Okay, so see you guys.